Hi everyone, my name is Neha and this is the 16th lecture on Introduction to Automation. In this lecture, we're going to continue the permanent magnet DC motors and we will learn about the control circuits of the DC motors. Now let's first start with this topic, which is reversing the permanent magnet motors. And to reverse the permanent magnet motor's direction, the polarity of the applied voltage must be reversed. As you can see in this picture, the op-amp is connected to the motor, and from here the control voltage is given. So the driving voltage here, so if the driving voltage is positive, then the motor will turn in the clockwise direction. And if the driving voltage is negative, then the motor will turn in a anti-clockwise direction. LM12 power op-amp you can use, and this is capable of providing the positive and the negative output voltage. So in this particular case you can use this type of op-amp, but in many applications this drive op-amp it cannot produce both positive and the negative voltage. So in those cases the switching circuits must be added to reverse the direction of the motor. So let's see those. So you can reverse the direction of the permanent magnet motor by using the relay. So as you can see here, double pole relay has been used. So these two relays are CR11 and CR12. CR11 has two terminals. These are the two terminals, and CR12 has these two terminals. So initially when the positive power supply is connected to this terminal and the negative side is connected to this terminal of the second relay, then what is happening here? The motor is having the positive supply from here and the negative supply from this side. So in that case your motor, it will rotate in the clockwise direction. Now if you want to change the direction, then by simply putting the contact to the other side of the terminal, you can change the direction. So if you put this contact to this terminal, and same with this one to this terminal, then what is happening? In that case the negative is supply will go to this terminal of the motor, which is A terminal, and the positive supply will go from here and then to the B terminal. So in that case, when your B side of the motor is positive and A side of the motor is negative, in that case your motor will turn in a counterclockwise direction. So that's how it works. Now let's see further. So further we have a solid state device which can be used in reversing the motor. The entire switching operation, it can be performed in a single IC, and one such example is given here of Allegro A3952, which has a supply voltage up to 50 volts with 2 ampere of output current. So this is an example of that. And on the right you see the circuit where the 4 FETs has been used. Q1, Q2, Q3 and Q4 are the 4 FETs, and with the help of that with the help of these 4 FETs, the direction of the motor can be changed. So what will happen when the transistor, this FET, a field effect transistor Q1 and a field effect transistor Q4, when they are turned on, or we can say when the switch is closed in these two and the switch is open on these two, on Q3 and Q2, then what will happen? The power supply will get it from here and the motor will start rotating in this direction. So this will be the direction of the motor. Now in the second case, if Q1 and Q4 are turned off and FETs Q3 and Q2 are turned on, which means they are forming a closed circuit, and current will start flowing from here and then further to here and then going to here to the ground. So in that case the direction of the motor will be in this way. This will become positive and this will become negative. And in the previous case, when the current was flowing from here, this was the positive and this was the negative. So that's how the current flow takes place in this type of circuit, where you use the solid state device, which is here is the field effect transistor. Now if you notice in this IC, it is also using 4 transistors. So this is the first, second, third and fourth. So all these 4 transistors, they are controlled by the internal logic and they operate in the pairs. Now next we have DC motor control circuit using the pulse width modulation. This pulse width modulation is a very effective approach in controlling the circuit, and in this, when power is supplied to the motor, it produces a square wave signal of constant magnitude but with varying pulses. Pulse width modulation, it offers 2 distinct advantages over the analog drive, and those 2 advantages are these. First, it does not need digital to analog converter because the pulse width modulation, they are digital in nature, so the power is going to be either on or off, so it can be controlled directly from a computer with a single bit. So hence eliminating the need of having the digital to analog converter. And the second important advantage is that it uses a class C amplifier, which is very efficient. In this type, the conditions that causes the power dissipation, those are actually minimized by using the class C type of amplifier. Now let's see the operation of the class C amplifier. So in this amplifier, let's assume that initially you are sending the 2 volts voltage from the base terminal to the transistor. Then what will happen? So in that situation, your transistor Q1, this Q1 will be turned on, and then collector current will flow freely through the motor. And the second case is when you are sending 0 volts through the base to the transistor. Then in that situation, your VCE is going to be 0 volts. So when VCE is 0 volt, then the entire line voltage is going to drop across this motor. In that situation, if you calculate the power, you can calculate by this formula, P is equals to VI. So I is our IC, and V is our here voltage across this transistor, which is 0 volts in the second case. So you will put the 0 volts, and then whatever is your IC, you will put it there. So if you have the 0 volts, then you will get the 0 power. What does it mean? It means that almost no power is lost by the transistor when IC current is flowing. So this is the advantage of using the class C amplifier. Now see next. Here you see the pulse width modulation input voltage and current waveform for 2 different duty cycles. So this one is for the long duty cycle and this one is for the short duty cycle. So if you notice, then this current is actually following the voltage waveform, but in the current waveform, due to the inductance of the motor, it is restricting the current from changing very fast, that you can observe from this waveform of the current. So you can see when the voltage is high, at that time the current is also increasing, but here the voltage is instantly changed from a higher to a lower voltage. So for current, it will take time to to go to a lower value. If you see on the right waveform, you will notice that for short duty cycle, these pulses they have become very small. So once these pulses are short, the relative peak to peak value of the current also increases. So like any periodic waveform, this current waveform you see here, it will have 2 important components, which is the RMS current and the average current. And the difference between these 2 values, they get larger as the pulse gets shorter. So if you notice, the difference here is much larger between the IRMS and I average, whereas when you have the long duty cycle, this difference is small. Now if you notice here, this torque equation which is given is proportional to the I average current, whereas this power dissipation is proportional to the IRMS value. So for the short duty cycle, as the IRMS current increases, then they have the proportionate relationship. It means that armature losses are also going to increase. So with shorter duty cycle, there will be more armature losses. Next, we are going to see the pulse width modulation control circuit, which uses a special type of programmable timing circuits, which is built into the microcontroller. So let's understand the circuit. So here this S3 and S1, they makes up a oscillator, and the 3 millisecond one shot, this triggers to the 1 millisecond one shot, and then which feedbacks to this again here, and then triggers the 3 millisecond one shot trigger, and so on. This will continue. So basically at the output of this this S1, you will get pulses that are high for 1 milliseconds and low for 3 milliseconds, and that you can see over here. This S1, you can see this is high for 1 millisecond and low for 3 milliseconds. So the total cycle is of a 4 milliseconds. So if you see here, full cycle is of 4 millisecond, and at the output of this you have 1 millisecond high and rest is off. Now secondly, if you notice this one, 2 millisecond one shot to OS2 here, it creates a 2 millisecond pulse and is triggered by the falling edge of the OS1. So if you see here, this is coming from here, so this will trigger at the falling edge and then produce a pulse of 2 milliseconds, and the output of this is going to be 1/2 of the 4 milliseconds, and which you can see here. So this is off for 1 millisecond and then on for 2 millisecond and then again off for 1 millisecond, so which is your half speed. Now at the output of this S3, it will create, so it will go into this C AND gate, and this will have this will be off for 1 millisecond and it will be on for 3 millisecond, because you can see here it says 3 millisecond, so it will be on for 3 millisecond and off for 1 millisecond. Now these gates which you see here, A, B, C, these are AND gates, and they are the control gates, and here you see our direct signal is going to this last gate, which is our AND gate, and which will provide the full cycle of 4 milliseconds, and this is for full on. And if you notice here, this is the controller, and that controller could be your computer, which would use 4-bit data to latch the output port with a 1 in the bit position of the desired speed, and the motor would operate at that speed until a new command is sent from the controller. So this was the pulse width modulation control circuit, and this is the end of the lecture. Thank you so much for watching.